All right, welcome back. Hope you are all rested somehow. Drink some coffee. This is the last talk of the day. Some announcements. Well, we have the list for the dinner, and you can only go to the dinner or have the discount for the dinner if you're registered. Okay. Otherwise, don't sit in our table. Okay. And it's my pleasure to introduce João Ramos, recently hired by IMPA, which is a plus for the country. And he's going to talk about Fourier uncertainty and the Klein-Gordon equation. Please, João.
Okay, so thanks, Felipe. So yeah, it's great to be here. I have been back to Brazil for 3 months already. And this is the first time that I speak about math in a talk in IMPA. So although my official kind of first colloquium in IMPA is in 1.5 months, this counts as an unofficial one. So let's dive into this. So as you can see, we're going to be talking about Fourier uncertainty and the Klein-Gordon equation. And we have to kind of explain both topics as we go. So the plan of the talk is simple. We're going to be seeing some aspects of Fourier uncertainty and how they came about, how they have been developing for the past years. And right at the end of the talk, so the plan is to see a bit of the Klein-Gordon equation and how it all connects. Okay? So let's start with, a very, it's a very crucial question, which is what is Fourier uncertainty, right? So maybe the best way to state this is by defining the Fourier transform and recalling, or maybe it's the first time that you're going to see this inequality, which is also known as the Heisenberg uncertainty principle in its Fourier analysis version, right? So what does this inequality say? So this inequality says that if I take any functions in L2, it's L2 norm squared. It is bounded by this constant 4 pi times this weighted L2 norm with this weight here, x minus x naught squared of f. And on the other hand, I get something of the same kind with f hat, right, with psi minus psi naught. Okay, and the fun thing about this is that you can take x naught and psi naught to be anything you want. And in particular, so let's imagine that the support of f is very tiny, okay? So the support of f is maybe like in an interval of size, say, epsilon. Then this x minus x naught is at most, I don't know, epsilon or something. So this is epsilon squared. It comes out as an epsilon. If the support of its Fourier transform, on the other hand, is of size delta, then this psi minus psi naught for the support of f hat, then, well, this is at most delta, so an extra delta comes out. So what we can get from this inequality is that if the support of f and the support of f hat are simultaneously very tiny, then I'm going to get that this right-hand side is majorized by 4 pi times epsilon times delta times the L2 norm squared again. And again, if I suppose that my function is not 0, then, well, 4 pi times epsilon times delta has to be at least 1. So if epsilon and delta are sufficiently small, this cannot be unless the function is 0, right? So a consequence of that is that, well, we can recover any function in L2 as long as we're given information on it outside of a tiny interval, A, and information on its Fourier transform outside another tiny interval, B, right? So that is another way to reinterpret what is being said here. And even another way to interpret that is a way from quantum mechanics, which is, well, if we try to measure, to localize, if this is in any shape or form, like the wave function of a particle, if we try to localize its position, then the Fourier transform here, by using Plancherel, this is actually measuring how much we localize the momentum of a particle. So you cannot localize both at the same time. So this is just tying back to quantum mechanics quickly. Okay. So this is perhaps the most basic form of uncertainty principles that we're going to see in this talk. Well, in order to show you guys that there's more to this uncertainty realm than this, let's maybe take a look at a few examples. So this inequality that we just saw is related to a couple of theorems. The first of which is the Paley-Wiener theorem that we saw in the previous talk already. So basically, a consequence of the Paley-Wiener theorem that says that, well, one of the implications of the Paley-Wiener theorem says that if f is a compactly supported function, then its Fourier transform is analytic. If the Fourier transform is analytic, then, well, let's suppose that we have two functions. We know both of them, that they agree outside of a compact set, and you know that their Fourier transforms agree outside of compact sets. Then this Paley-Wiener theorem, just due to analyticity, well, we know that, well, if an analytic function is 0 on a set that has an accumulation point, then it has to be identically 0. So from this theorem, we get immediately that given those properties that we just had, then f is equal to g. So we can recover a function. So we cannot localize a function, in other words, to an interval, to a compact set, while simultaneously localizing the Fourier transform to a compact set. So this is an immediate generalization of what we saw in the previous slide, right? Another nice result that we should highlight is the the Benedict-Amheim-Bétier uncertainty principle, which says that actually this previous one that I just mentioned, it can be even further generalized. Okay, so I was talking about compact sets. Forget about that. I just give you two sets A and B that have finite Lebesgue measure, right? Then the L2 norm squared of a function, it's bounded by a constant that depends on the two sets, but it's a finite constant that does not depend on the function, times the L2 norm of the function outside of the set A, plus the L2 norm of the Fourier transform outside of the set B. In other words, I cannot even localize my function to a finite measure set. Like, it's not even a matter, it's like the topology of being compact, it does not matter. Being finite measure, I cannot localize a function and its Fourier transform simultaneously to finite measure sets even, right? And maybe like what I'd like to think about, as kind of the ultimate generalization of this result, it's Hardy's uncertainty principle, right? Which doesn't even say anything about the function vanishing or being determined. I add an additional layer of uncertainty on top. So if I say, well, let's forget about determining my function outside of a set. Let's say that, well, I know the function up to a Gaussian error, right? And I know the Fourier transform up to a Gaussian error as well. As long as the Gaussian is the standard Gaussian with pi in the exponent, then what I know is that my function itself, if I know this function, then it can only, so if I know the function up to a Gaussian error on both sides, then what I know is one given function plus a Gaussian itself. So in other words, I cannot localize my function as much as a Gaussian in both Fourier and space without forcing my function to be identically 0, right? So if I, let's for instance think that I put a slightly larger constant a here, like my function decays like e to the minus a pi x squared with a larger than 1, and the Fourier transform decays like the standard Gaussian. As a is larger than 1, this result would imply that my function is a kind of Gaussian, but, well, it decays faster than the standard Gaussian, so it should be identically 0, right? So we get this kind of result that says, well, in order to kind of say that our function is only determined from like a few kind of samples, a few kind of a little information. We do not even need precise information outside of compact sets, outside of sets of finite measure. Even a Gaussian error is allowed. And then maybe the take home from this slide is that, yeah, it's exactly what I said. If sufficient information is given on space and frequency, then I can recover my function. Or in other words, I cannot really localize my function a lot in space and frequency without making my function vanish identically. Right? Okay, so this was a crash course on classical uncertainty principles. Let's go to more modern results. And I always like to talk a bit about a very fashionable topic, which is the sphere packing problem, right? So, yeah, so this, many of you might have heard of this problem. Maybe a little introduction to, well, the at least the Euclidean version of it. So let's take a collection of infinitely many disjoint spheres in Rn of radius 1, right? So let's say that I give you the freedom of arranging them however you want. And I give you the task of, look, you have to cover as much space as you can with these spheres. What is the amount of space that you covered in the end? And this is exactly the formulation of the problem that we're going to be interested in here. And for instance, in dimension 2, two possible packings that you could choose for your task of maximizing the area covered are these. So this is the square packing, so it's kind of associated to the integer lattice in R2. And this is the hexagonal packing, which is associated to a different lattice, also in R2. And both of them are examples of sphere packings, and it's kind of like it's intuitive to see that this one does a better job than this one at covering space, right? So the space outside of the balls in my packing here, it's actually larger than this one. And this problem is actually related to the problem of universal optimality, which is kind of a dual version of this. So the problem of universal optimality says, it actually asks for, well, let's say that we're giving like some sort of potential function that it's kind of radial, it depends only on the distance of the points, it's decreasing, and we know that the densities of the particles that we're dealing with is fixed, right? So we're giving a bunch of particles, we know their density, and we know what is the minimal, what is the best configuration for these particles according to this potential energy, right? So that minimizes this kind of sum. And it's not too hard to see, so it's basically a lemma that you can work it out, that if you take like the indicator function of 0, 2, then you can recover exactly the sphere packing problem from this universal optimality problem, right? So these two problems are quite intimately related, and well, the latter one appeared so far as a motivation, but it's going to make a comeback in a while. So let's maybe take a look at instances where the sphere packing problem has been solved, because, well, there's not that many. So the first of them, which is not even there, is dimension 1, which, well, you just put intervals, one next to the other, you cover everything, there's not much to do. And the second one, where it's dimension 2, where things get a little bit more interesting, but it's been kind of known in the literature, but not really proved until like Fejestot in 1942 gave a rigorous proof of that this packing here, the hexagonal packing, is the best possible in dimension 2, right? And he also gave a stability version of that result. In dimension 3, things get a little bit, or let's say a lot out of control, where we have this kind of arrangement, which is basically how you would stack oranges in a supermarket, or another way to describe that is putting like layers of hexagonal packings on top of each other. It's the best packing possible, but it's actually not the only one. There's an uncountable amount of non-isomorphic, pairwise non-isomorphic packings, and completely saturated. You cannot add any sphere, you cannot make it denser, that actually do realize the same bound. So they attain the same thing. And this was actually, there's an interesting story behind that. I think this result was first proved in, I think the first attempted proof is in 1997 and published in 2003. But it was computer assisted and people did not fully trust it until 2015 when Hales finally decided, hey, let's check this thing actually with the computer in a formal, rigorous way. And in 2015, they published, I think Hales with several co-authors actually managed to show that this is, well, there's a formal verification, a formal, like there's a, you can run like several computer algebra softwares that verify this for you. And maybe the two dimensions that are relevant for us are dimensions 8 and 24, right? And this is due to the breakthrough work of Marina Wiazowska. She was my postdoc mentor for a year in Lausanne. And Marina, what she did was she managed to show that these two very particular structures, the E8 lattice and the Leech lattice, this lambda 24 lattice, they do the best possible jobs. In dimension 8, she came up with a proof. And then I think this, how the story goes is as follows. She had an almost complete proof in dimension 24, but there's kind of like a gap right at the end, and then the Kohn, Kummer, Miller, and Radchenko came in and helped her, and they managed to finish the proof. So it's a collaborative effort in dimension 24, and in dimension 8, it's the original breakthrough by Marina. So let's maybe look a little bit deeper into these two dimensions, right? So these two dimensions, so these two structures, the Leech lattice and the E8 lattice, so they can be characterized by the following properties, right? So they're both unimodular lattices. So that is, the volume of this fundamental region that the lattice induces is 1. Another kind of defining characteristic is that the length of all non-zero vectors in these lattices is the root of an even integer, so they're called even. And in the case of lambda 24, the minimal length is 2. Okay, so that is these properties, plus them being like self-dual as lattices, they actually uniquely define these lattices. So these should be like, they're kind of like minimizing something. So the idea behind it is there's some minimization going on. They're the first of their kinds, and therefore whenever we have minimizers, we are expected that lots and lots of symmetry should go on. And this thing, and as you can see, like the group of symmetries of these lattices are actually huge, so they're very, so it induces one to think that packing spheres on them is somehow, it's somehow a good idea, right? But then that's, so the proof, funnily enough and beautifully enough, it's actually a Fourier analysis proof, and kind of like a bird's eye view idea of the proof is as follows. So what Marina did was she considered the work by Henry Kohn and Noam Elkies from 2003, where they actually showed that, well, if you give me a function f from Rn to R, the function is such that its Fourier transform is non-negative. The function itself, outside of a certain ball of radius R, highlighted there, the function is non-positive. Then, well, let me take the best R such that my function satisfies this property, and I'll tell you that the best packing density in dimension n, it's related to this R by exactly this formula. It's related to the R and to the function by that formula, right? Okay, so this is unfortunately I don't have time to show the proof of this, but it's a very nice, it's a beautiful Poisson summation formula proof. But what basically the upshot of that is, well, we can take, by scaling somehow, f at 0 and f hat at 0 to be equal. And what Kohn and Elkies did was they ran simulations and they showed that, if you run the simulations, R equals root 2 seem to be achievable for a certain specific function. So their simulations pointed at the existence of a function. They were getting some very good approximations to root 2. Some functions with this property that are such that their R's were approximating root 2 very well. And this induces, if there's such a thing with R equals root 2 in dimension 8, then by their Poisson summation proof, we can make sure that the E8 lattice is the best one possible. And that's kind of a similar thing for R equals 2 and dimension 24 with the Leech lattice, right? And if you open up what their proof gives you, and if you assume, if you have faith in the fact that R equals to root 2 should be the best possible in dimension 8, and that's roughly what Marina's 0th step was, assuming that f is radial, and assuming that root 2 is the best thing possible in dimension 8, then what she said is like, look, then all I need to find is a function f, which is radial in R8, such that its values at vectors of length root 2n, and its values of its Fourier transforms at vectors root 2n all vanish for n greater than or equal to 1. Its radial derivative vanishes at the same guys as long as n is greater than or equal to 2. And the radial derivative of its Fourier transform vanishes at all of those guys. And unfortunately, again, I don't have time to discuss Marina's beautiful construction. But then, after this big leap of faith of believing that such a function exists, she manages to use modular forms to build those functions, right? So this is kind of a picture of what the functions should look like, right? So they're clearly vanishing at guise of the form root 2n. And, you know, it's kind of a sensible thing that their radial derivative should vanish, right? Because if f hat is non-negative, whenever it's 0, it touches back the axis. So if it only touches the axis, you should induce naturally a 0 of the derivative. And the same thing for f. And as you can see in the top part of the slide, so the natural question that comes from this is, well, it's so good. Marina could solve this with this beautiful construction. She could solve the problem of determining a function, of finding a function from the values, from these values, as long as they were this very specific sequence that was composed mostly of zeros, right? So there's only one value, which was f prime at root 2, that was not 0 from this set, right? And then the question is, well, what if I give you a more general sequence that decays as fast as you'd like? Can I still build my function back? Can you not? What are the obstructions? What can be done in that case, right? And this is a great result by this same team of collaborators that I said, Kohn, Kumar, Miller, Radchenko, and Viazovska, where they actually showed that, well, even an interpolation formula exists as long as that sequence is nice enough. And you can recover any radial Schwartz function in dimensions 8 and 24 from those values. This is an amazing result. And actually, as I said that the universal optimality problem would make a comeback, they managed to solve the universal optimality problem in those dimensions 8 and 24 by using that theorem on top. So this is an amazing result. It's published at Annals of Math, and I think it appeared a couple of years ago. And it's related to another one of my favorite theorems in math, which is the Radchenko-Viazovska interpolation formula, which basically says that the same thing can be done, but without the whole derivative thing in dimension 1. So it basically says that, well, if you give me a nice Schwartz function that is even, then I can recover it explicitly from these guys. So from the values of f at root n, the values of f hat at root n. So basically the formula that we get is something like this. So f at x, it's a sum of f at root n, an of x, plus the Fourier transform of f at root n times the Fourier transform of an. And here n is greater than or equal to 0, and we have to suppose that f is an even Schwartz function on the real line, right? And as I said, this is an amazing result, and it's amazing that this result was first appeared on Archive in 2017, and it was not known by some random mathematician in the 30s or something. It's for me, it's shocking, this fact, but it's beautiful at the same time. But finally, I have to mention a very nice result that also appeared recently, is that, well, if we're talking about determining a function from discrete values, then we have to mention this recent results by Kulikov, Nazarov, and Sodin, where they actually managed to get a similar result. Perhaps the only difference is that it's not an explicit interpolation formula, but they do get an interpolation formula as long as their sequences are, well, they're different than root n, but they behave like powers of integers of a certain kind. Okay, so that is like, so it's, and basically the main difference between these results that I was talking about before and this one is that the ones before, they rely on rigidity and modular form constructions, and this last one is a purely analytic result, right? And just before we go into the last part of the talk, let me just emphasize, so I think it has not been made super clear what the relationship was between this first part and the second, but bear with me for a while. if you see like this problem of, well, you know, a function vanishes on a certain set and its Fourier transform vanishes on a certain set, then the function is identically 0. And the problem of determining a function from discrete samples are basically the same, right? So let's suppose that I determine the samples to be all 0, right? So I'm basically saying the same thing. But whereas in the previous context, in this classical uncertainty realm, I was talking about continuous measurements, so there's like Gaussian decay everywhere. I was talking about saying that a function is identically 0 outside of a compact set, and it's Fourier transform as well, and recovering it. Whereas here I'm saying, look, I'm not giving you continuous levels of measurements. I'm just saying, like, I'll give you the fact that the function vanishes at root n, and the Fourier transform vanishes at root n. Does this imply that the function is identically 0? And what these results, what is beautiful about these results is that the answer is still yes. Is that, for instance, if I say that these are all 0 and these are all 0, then the function is immediately identically 0. I think that's really powerful, right? And that's really striking. Okay, so before we move on, do you have any questions? Well, if not, I'll go on. Okay, so let's talk a bit about Klein-Gordon and uniqueness properties of Klein-Gordon and how it all ties up with the remainder of the talk. Okay, so what is the Klein-Gordon equation? Well, this equation that I'm stating there is what I'm going to be referring to as the Klein-Gordon equation, although like most likely if you know what the Klein-Gordon equation is, you're probably wondering why I'm not writing something like this. Well, I'm just taking a rotation in dimension 1 or dimension 2, as I'm mentioning there. I mean, taking time and space to be the dimensions that I'm working on. Just taking a rotation of this equation yields the one on top, so I'm going to be working with that one, okay? So let's say that I want to solve that equation. If I want to solve that equation, then, well, you know, let's treat it. I know that it's not really like a purely evolution equation, but let's treat it as if it was. Then if I say that, okay, my function restricted, my solution restricted to the real line has some sort of smoothness, then I can, as a matter of fact, solve this equation by using Fourier inversion, and the formula is here, right? It's this very kind of weird formula that I need to know the Fourier transform of the restriction of my function to the real line, which is a usual thing if I'm working on dispersive equations, for instance. But here I have kind of this weird exponential where my symbol is 1 over t, right? Which is induced by this kind of like double cross derivative in x and y. Okay, so my solution is given explicitly by this formula. And in particular, if I let g of t be the Fourier transform of the restriction of u to the real line, then my solution at the x-axis, at the real axis, is going to be just the Fourier transform, the scaled Fourier transform of g, right? So it's just my function f itself. So now I'm sorry about the change of scale in the Fourier transform. Fourier transforms are now going to be with this pi normalization instead of 2 pi because it's going to make things it's going to make the algebra slightly more convenient. But the nice thing is that in the y-axis, we have also this kind of like pure kind of e to the pi I y over t exponential showing up. So I don't have this kind of weird cross term where I have x t plus y over t showing up. Okay, so this is the Klein-Gordon equation, and you now know how to solve it. You know how to compute it on the compute solutions on the x-axis and on the y-axis. And what I need to tell you is that in their celebrated 2011 paper, Heidenbaum and Montes Rodriguez showed that if I'm given the values of these solutions at a certain subset of the x-axis consisting of a rescaled version of the integers, and the same at the y-axis, and if the product of the scaling is at most 1, and that's where the normalization of the Fourier transform comes into play, then my solution is identically 0. And if the product of this scaling is at least 1, then we can find counterexamples. That's what they showed. So a picture of these sets as illustrated here. So it's like I have Z and the x-axis and Z and the y-axis. If, for instance, I take alpha and beta to be both 1, right? And as you can say right now, well, yeah, okay, João, that's all well, that's very cool, but where the hell are the uncertainty principles, right? You just all of a sudden started talking about Klein-Gordon equation where you're talking about Fourier uncertainty principles is getting confusing, right? Well, actually, let me try to motivate that with an explicit example. Okay, so suppose that U has a solution as before that vanishes at one of those rescaled, what we call a lattice cross, right? So then take, well, let G be the Fourier transform of its restriction to the real line, and let psi be the function in R4 defined by this integral here, with this kind of factor 1 over modulus of x squared up front. So if I define this function, it's clearly, well, it only depends on the modulus of the vector x, so it's a radial function in R4. And if we take a 4-dimensional Fourier transform, then something kind of weird happens, which is that, well, if we take a Fourier transform of a Gaussian, it should be a Gaussian, but I should invert kind of like the intensity, right? So I get something like this. Well, I'm dividing by this 1 over x squared factor, but this actually also behaves well with respect to the Fourier transform. So if I just do all the computations, I get that the Fourier transform has exactly this form. And it's not a coincidence. Let me just show you guys again what we had in the previous slide. We had e to the ixt and e to the iy over t here. And here we get e to the I pi x squared t, e to the I pi y squared over t again. So I'm getting something that is eerily similar to what I had in my Klein-Gordon context before. So the bottom line is, if U is a solution to the Klein-Gordon equation and G is the restriction, the Fourier transform of its restriction to the real line, then if I build this psi, then it vanishes on spheres of radii root of alpha n, and its Fourier transform vanishes on spheres of radii root of beta n, right? So because if I just plug root of alpha n here, I'm going to get alpha n times t, and that's exactly the set of points where I said that my solution was vanishing, and the same thing here below. But this is similar to a result which we already have seen. So we saw this Radchenko-Wiazowska interpolation formula, which is on the blackboard and there as well, which says that if my function vanishes on, like it's not spheres because it's dimension 1, but there is a suitable analog of that result in higher dimensions as well. But if my function vanishes on points of the form root n, its Fourier transform vanishes on points of the form root n, then the function has to be identically 0. We just got a scaled up version of that here in this function. Right? So if we manage to show, like for instance, let's suppose that we have a higher dimensional version of that result. We show that any function that vanishes on these spheres has to vanish identically. Then this function psi would have to vanish identically. If it does, then the function g that gave rise to the function psi has to vanish identically, and hence the function u vanishes, right? So we get a result for Klein-Gordon from a Fourier uniqueness result. So that is why I said that everything was connected, right? So that I can connect explicitly through this kind of magic trick, Fourier analysis and the Klein-Gordon equation. Well, to an extent that is like further than what meets the eye. Okay, but this actually, yeah, as I said, this hints to a deeper connection, right? And to which extent this actually holds. And actually, there's a very nice recent manuscript by Bacán, Hedelbaum, and Montes Rodriguez, where they actually showed that you can actually prove the Radchenko-Wiazowska interpolation formula by just working with the Klein-Gordon equation. Right? So what they did was they showed that something that they call this kind of hyperbolic Fourier series expansion works. It holds for, in a suitable sense, for any distribution f. Of course, this has to be made sense of, right? Because you cannot, it's not a function, it's a distribution, but hey, if you make sense of that in the right way, these two things here coincide, both sides in this equation. And this actually induces much more, right? So if we look at it from from purely the Klein-Gordon point of view, then actually we can get interpolation formulas for the Klein-Gordon equation from discrete sets, right? So there are actually some special solutions, V n naught and V naught n, such that any solution to the Klein-Gordon equation with some mild assumptions can be recovered from the values at the lattice cross, multiplied by this V n naught, V naught n, and summed up, right? So it's very similar. So if you take a look at the formula on here and the formula on the blackboard, they're very similar, right? So it's the same kind of formula. But there are some drawbacks. So the drawbacks are, so the equivalence that I told you guys, it actually only holds if I'm working exactly with a scaled up version of the integers. If I forego this kind of assumption, if I no longer want to discuss uniqueness results for the Klein-Gordon equation on something like alpha times n or beta times n on the y and x-axis respectively, then, well, I can no longer use this kind of equivalence. This actually supposes that my functions are all even, such that this whole Fourier transform trick can work. So what can we do? And that was exactly what Hiddenbaum and Montes Rodriguez in their celebrated paper, what they asked. So what they asked was, well, what if we let an and bn fluctuate a bit, right? So if we let them fluctuate a bit, and along this lattice cross, can we still recover some sort of result? This would actually, what would this mean in practical terms? This would mean that we would have to find a proof that does not really rely on the algebraic side of things, right? So because this proof by Hiddenbaum and Montes Rodriguez actually really relied heavily on the fact that we're dealing with the integers. Here we have to abandon that immediately. And then a case of particular interest for them was that of translated lattice crosses. So if I take the same kind of lattice crosses that they were considering, but now translated by parameters theta 1 and theta 2, I already lose the effect of my sequence being even, and they don't know what to do in that case either. They don't know what are the exact conditions for of a solution to be 0, and a new theory seemed to be needed, right? So very quickly right now, these last 10 minutes, I'd like to discuss my contribution to this topic, which is a solution basically to this previous topic, and this is it's a good time to say that it's joint work with Danilo Radchenko. And what we did was the following, right? So the first assertion there says that, well, basically take two sequences, an and bn, and suppose that their maximal spacings are alpha and beta, and that the product of the maximal spacings lies strictly below 1, right? Then the only solution to Klein-Gordon such that its restriction to the x-axis lies in L2 and vanishes at this kind of perturbed lattice cross is at U identically 0. That's the only solution. We can still recover. It's an affirmative kind of answer in this alpha times beta less than 1 case to their question. And right now, let's suppose that we have a kind of a different control on the spacings, right? Let's suppose that the spacings are bounded from below, that they're products of this kind of minimal spacings are at least 1. Then we can construct non-trivial solutions to this Klein-Gordon equation that vanish at those points, right? So it's kind of like, except for the fact that it's kind of annoying, but it's kind of necessary in our proof, we can relax this a bit to, instead of having sup and inf, we can relax it to being lim sup and lim inf. But it's kind of annoying that we have sup and inf, but it's almost a sharp condition there, and it's sharp in the sense that we have, well, for alpha times beta less than 1, something holds. For alpha times beta greater than 1, something else holds, right? And finally, as I was hinting at before, we have these translated lattice crosses. And in the case of translated lattice crosses, actually our result is completely sharp. As long as the restriction to the real line is in L2, then U being identically 0 is equivalent to alpha times beta being less than or equal to 1. No condition on theta 1, no condition on theta 2. This is an absolutely sharp result. Okay, so for the 8-9 minutes that I have left, I'd like to discuss the proof of these two parts, and for the proof of that, you guys will have to check the paper, but I'm happy to discuss as well. So let's maybe start with the proof of the first one. So, but before that, here's a little illustration with these sequences. You can see that the gaps are slightly irregular, but as long as we have some sort of bounds, we can still, so the bottom line is we can still get something, right? So for the proof of the first assertion, we'll start with writing up our formula for the solution of the Klein-Gordon equation, right? So it's u of x and y equals to this integral here. And by scaling, so if alpha times beta is less than 1, if we employ the correct scaling, we can suppose that both of them are equal and less than 1, okay? So the first step, which is a technical step, basically says that, well, if I use the condition on the zeros that the maximal spacing is, well, right now that I normalized everything, it's at most 1, and that my restriction to the real line is in L2, then I actually gain regularity. It's kind of like, so the idea behind it is kind of like it's kind of like a PDE property of this thing, right? So G is, if you will, if you don't recall, this is the Fourier transform of the restriction of U to the real line. So G being in this space here means that the restriction of the real line of my solution is actually, in a sense, differentiable, right? So if I start with something only in L2, I gain a little bit of regularity. So this regularity is precious to us because, well, what we were going to be using right now is this Poincare-Oettinger inequality. So if we have this bit of regularity on G hat, then we can talk about its derivative. And if we use the Poincare-Oettinger inequality, since we know that U vanishes at the intervals an plus 1, then the Poincare-Oettinger with sharp constant gives us this part here, right? Which is this part here, sorry, in the bottom. And this part here is trivial since the gaps between consecutive terms are at most 1. So I get, the bottom line is I get that this right-hand side is less than this left-hand side. Okay, so what do I do now? I sum it up in n and use Poincaré. So by Poincaré, with my normalization of the Fourier transform, I get that this left-hand side equals to this, which by the previous slide, if I sum it up, I get exactly by Poincaré this thing. Okay, so I got this inequality that the integral of t squared g of t squared is greater than the integral of g of t squared, right? But right now, the catch is that I'm going to do the same thing for this other function, 1 over x squared, g of 1 over x. And the nice part about this function is that its Fourier transform is the restriction of u to the y-axis. So I use this exact same inequality, I get the exact same conclusion, but hey, I have a relationship between f and g. If I change variables, I get that this integral here is the integral of g, and the integral of f is the integral of g with the weight. So I get that the integral of t squared g squared is greater than integral of t squared g squared, which is a contradiction unless g is identically 0. So very neat proof. We managed to show our result, right? So the first part of the result is done. Let's go to the next one, which is the construction of counterexamples. And let me try to give you guys an idea of what the construction looks like. And for that, we just define, so we take an L2 theta, function theta in L2, and consider this map T that is basically this weird kind of skewed Fourier transform of T. So the bottom line is that this map, since, if you recall that, so the bottom line of this is making rigorous what we have already seen in this psi map before. So this psi map from before It was a radial function. We used some Fourier uniqueness results for this psi map, but he used heavily the fact that the sequences were even. Right now, I'm still getting something that induces a function in R4, but then if I try not to work with even sequences, I need to be a bit more careful, so I need to define this kind of big theta plus and minus functions, which depend on my original theta on the negative and positive axis. But the bottom line is that this operator t, it's very intimately related to a 4-dimensional Fourier transform again, right? So basically what we want to do is, if we take a look again at what our function u that we're seeking must look like, it's something like this. So the problem of constructing u that vanishes at those points actually reduces to constructing two functions, theta plus and minus, that patch up nicely. They're radial in R4, and they vanish at points of the form root of modulus an, and the Fourier transform vanish at points of the form root of modulus bn. And by using, again, a very nice result that I mentioned, I alluded to before, by Kulikov, Nazarov, and Sodin, actually don't use the result, we use the techniques behind the result, we managed to show that constructing such functions is possible exactly when this kind of condition is fulfilled. So we managed to construct these functions. Patching them up is not particularly hard. It turns out that this map T, it's kind of it does several wonders in the middle of our exploration. So they patch up very nicely. Basically, if one function is supported on a half line, this map T maps to something that is supported on the opposite half line. So patching it up it's an easy thing. But yeah, but that's basically everything that I wanted to discuss with you guys today. As I said, yeah, this finishes the proof of the results. The last part, unfortunately, I think I wouldn't be able to explain in 1.5 minutes, so you guys are going to have to check the paper. Thank you so much.